Give me space. I need space, she says. Oh yeah? Well, you tell me, what is space exactly? I've been doing some reading lately, watching various science videos, trying to come to grips with some aspects of modern physics. Not very successfully, by the way. I've been trying to understand, for instance, what space is when you're dealing with Einstein's general theory of relativity. And of course, what gravity is, and how the Einsteinian model of gravity fits in with quantum theory. You know, just your normal everyday questions. I haven't even started on the really difficult questions, such as what the hell is quantum entanglement? I reckon if you lived towards the end of the 19th century, the average layperson would have been able to acquire a reasonable grasp of physics. Maxwell's electromagnetic equations may have given a little trouble, but by and large, I think physics was within the grasp of the layperson. It made sense. It wasn't far removed from common sense and what the average person could observe taking place around them. That all changed at the beginning of the 20th century, first with Einstein and then with quantum theory. Suddenly none of it made sense, or at least not common sense, and suddenly the world around us is no longer the real world. Everything was mathematics now, equations, and now the real world could only be described in verbal language via metaphor and analogy. Protons and electrons were not actually particles. They behaved like both waves and particles, depending on the conditions. No, they no longer actually are particles in the way that we sometimes depict them, like tiny ping pong balls. Nor are photons, for instance, actually waves. More like, maybe, packets of energy. No, protons, electrons and photons and so on, these behave like particles or like waves. It's an analogy. Their behaviour is, under certain conditions, like that of the things that we call particles, or like the things we call waves. Ultimately, these units of the quantum world are solutions to equations, not things as we experience them in the macro world. This puts much of modern physics beyond the reach of us mere mortals. Don't feel too bad though. Even mathematicians still struggle with some of Einstein's equations. I believe even Einstein wondered from time to time whether his equations had any real solutions or whether it was all just nonsense. However, one of the solutions was what later came to be known as a black hole, although the first actual black hole wasn't identified until 1971. The fact that his equations predicted black holes nearly 70 years before they were actually observed is pretty strong support for their validity. But I digress. There are, as you may or may not know, some fundamental inconsistencies between relativity theory, which clearly works at the macro level, and quantum theory, which works at the micro level. The search to reconcile the two theories has been long, and up to the present time at least, unsuccessful. Now, anything I say past this point may be wrong, probably is wrong. It's all a bit tricky. But here goes, and I'm just touching the surface here of a couple of issues. First of all, Einstein's model of gravity and space-time supersedes the Newtonian model of gravity and space and time. Note that with Einstein it becomes space-time, not space and time. Secondly, gravity is not a force. Gravity is the curvature or distortion of space that's caused by the presence of matter energy. This curvature then determines the motion of matter through space. What we call falling is just matter following the curvature of space. Note that gravity is not a force that curves space-time, it is the curvature of space-time. So if in the Einsteinian model gravity is not a force, what's the point in quantum theory of trying to understand gravity in quantum terms, as an exchange, for example, of hypothetical gravitons, analogous to the exchange of photons in the electromagnetic force, or the exchange of gluons in the strong nuclear force. What's the point of that if gravity isn't a force? Are these physicists not talking to each other? Also, quantum theory is generally formulated, I believe, in terms of a Euclidean type of space, not a simple Euclidean space that we're used to, something more complicated, but nevertheless a Euclidean type of space, rather than the curved space-time of relativity. I may have this wrong, but I think there are attempts to formulate quantum theory against the background of Einsteinian space-time, and honestly, the discussion loses me here. On the other hand, I also believe there are attempts to quantize space and time, if not space-time, i.e. to demonstrate that time and space are granular rather than smooth, although both appear smooth at the macro level. Of course, if time and space exist only in little quantum packages, we're inevitably going to ask, okay, what are these packages in? What are they suspended in? What lies between these packages? Let's set that aside for the moment. So, if space-time is granular, why does it appear smooth to us? Think of this in terms of digital music. Digital music actually consists of individual packets of music containing various quanta of information which follow each other in rapid succession, so that to our ear the music actually sounds smooth. So at the level of which we are able to perceive and observe reality, what we call reality, space-time, it appears smooth to us. Okay, let's return to the Einsteinian model of space-time. What the hell is it? What is this something-nothing that is perturbed by the presence of matter-energy? It has to be a something, right? I think physicists are terrified of reviving the idea of the ether. Nevertheless, the way they describe space-time often sounds very similar to what people used to call the ether, a medium through which matter and light move. They won't use the word ether, though. Mind you, I'm not really sure that it would matter much if they did, as long as it was understood as an analogy, as a metaphor. We still can't really say what space-time is, but we can, it seems, describe how it behaves, certainly mathematically. Matter-energy distorts or curves space-time, and space-time then, in turn, determines how matter-energy moves. We shouldn't think of an object as falling along these lines, as if this curvature itself somehow imparted movement to the object. But if something else imparts energy to an object which subsequently moves, it will follow these lines of curvature. Clear? I haven't even touched on difficult issues such as time dilation in the Einsteinian model, or how an object can be in more than one place at the same time in quantum physics, or even knottier issues such as quantum entanglement, which I mentioned earlier. Often these things can only be described in mathematical terms, which most of us will never be able to understand. Any model we use to visualize these phenomena will always be as wrong as it is right. Fortunately, though, the mathematical equations often generate predictions which can actually be tested in the real world. If equation A is right, this will happen. If equation B is right, this will happen. The fact that we can't actually know the world the way it really is doesn't bother me as much as I thought it might. I guess that's because I've been far more influenced by the philosophy of Immanuel Kant than I'd realised. You see, Kant, as I've mentioned before, didn't believe that we could experience the real world directly, but only via certain a priori categories such as space, time, and causality. So, according to this philosophy, those categories and others are part of a pre-existing framework that determines how and whether we can experience anything at all, rather than actual properties of the real world. I always argue, though, that those structures emerged in this reality, and that, therefore, while the experiences we have of the world are not direct experiences of the world as it is, they are nevertheless accurate and consistent analogies of the world as it is. Otherwise, they wouldn't enable us to navigate reliably through this reality. Finally, and perhaps not entirely consistently, my own current provisional understanding of space-time is that it may be an emergent property arising from the underlying quantum structure of reality. It's an emergent property in the same way that life is an emergent property of a certain complexity and configuration of matter. I doubt that, prior to the emergence of life, its emergence would have necessarily been predictable. Similarly, consciousness is an emergent property arising out of the complexity and configuration of certain physiological, chemical, electrical processes taking place in the brain. Again, not something that's necessarily predictable before it actually appeared on the scene. At the quantum level, time, insofar as we can speak of time at this level at all, appears to be non-directional, unlike at the macro level where it clearly runs in one direction. So certain properties emerge from this unknowable quantum substrate, which we call things such as space and time, space-time, which are in fact knowable and observable by us. I think, anyway. Maybe.